Hi, everyone. Welcome to my lightning talk. My name is Sally Collins. I am a graduate student at Georgia Tech, and today I'm going to be telling you about the figure eight knot, the measure pattern, and smooth concordance. So thank you all in advance for coming to my talk, and thank you to the organizers for letting me speak. So unfortunately, we have to begin our talk with a wall of text. Luckily for you all, this lightning talk is recorded so you can pause and read these definitions at your leisure. So I won't get into too much detail, but the general theme of the question we're looking at today is exploring the relationship between the knot type of knots in S3 and the homeomorphism type of their end-framed surgery manifolds. And we're specifically going to be looking at the zero-framed surgery manifold, which I'll just call the zero manifold for the most part. So it's denoted as such. And then when I say zero manifold, that's what I mean. So I said knot type and homeomorphism type. So I owe you a bit more specificity. When I say knot type, we're going to be looking at knots up to smooth concordance. We're going to be looking at our three manifolds up to homology cobordism relative to meridians, which I will call homology cobordism RM to save just a little bit of time in this 5-minute recording. And that's right. So now we have a knot type and a homeomorphism type. And this work is inspired by a question posed in a conjecture of Kirby and Ocblut in Kirby's problem list. It's problem 1.19 and some subsequent remarks, where they conjecture that if two knots have the same zero surgery three manifold, then it must have meant that the knots were concordant. And in the case of this homeomorphism type and this knot type, this conjecture is false. And we know that this conjecture is false from prior results of Cochrane, Franklin, Hedden, and Horn, a paper in 2011, where they gave us a family of infinite order knots such that their three manifolds were the same homeomorphism type, but their knots were not the same knot type. Using those types we described in the page previously. So today I'm going to expand on that result and give you a pair of knots, the figure eight knot and Q41, which is the measure pattern of the figure eight knot. The measure pattern is a historically significant knot. It has winding number +1. And because of that, because it's a pattern with winding number +1, there's a result in that Cochrane, Franklin, Hedden, and Horn paper that tells us that automatically any knot and its image under a pattern with winding number +1, their zero surgery through manifolds will be homology cobordant RM. And so that result here comes automatically. And then it turns out the majority of the result I'm going to talk about today is this part here, that the measure pattern of the figure eight has infinite order in the smooth concordance group. And perhaps we already know that the figure eight has order too. So somehow this pair of knots is not only non-concordant, but their concordance orders are very dissimilar. How are we going to prove this? Well, here is the figure eight knot. We're going to look at its complement in S3. I hope you appreciate my artistic interpretation of S3 as this sort of amorphous blob. And here is the measure pattern in the solid torus. Here is a link that we get from that. We're going to look at the link complement in S3. And so we are going to use a floor theory, bordered floor homology, which is a floor theory for three manifolds with boundary that allows us to compute bordered invariants for these three manifolds with boundary, and then pair up our invariants according to how we glue our three manifolds with boundary along their boundary components. So we're going to glue this boundary component to the boundary component of this link complement that corresponds to the blue part, to the pattern. And we're going to pair up the bordered invariants. This is a 5-minute talk. I certainly don't have time to go into all the homological algebra involved, but suffice to say there's a lot. We get this tensor complex here to the right. We do a lot of homotopy equivalences, change of bases, and then we translate our bordered floor homology back into knot floor homology, and then we can do some involutive knot floor homology. Let me just say that having to talk about 3 different refinements of Hegardt floor homology in a 5-minute talk is no easy feat. So involutive Hegardt floor homology due to Hendricks and Manilescu makes use of this iota K map on the knot floor complex. And what we will do is show that Using an equivalence relation on iota k complexes, we can show that the major pattern of the figure 8 cannot have finite order in the smooth concordance group. Okay, I'm just about out of time, but here is my conclusion. Basically, my iota k complex is dual to a complex computed by Halm, Kang, Park, and Sofragen in 2020. So make reference to their result there and say, you know, this has infinite order. And here are my future directions. Again, you can pause this recording and check out those future directions if you find them interesting. I hope to see you at my office hours. Thank you for coming.